Welcome to Improper Integrals by Conceptual Calculus. An improper integral is an integral that involves infinity in some way. There are two types of improper integrals. In the first type, one or both of the limits of integration may be infinite. It is easy to tell that these integrals are improper because you can see the infinity symbol. In the second type, the infinity is less obvious. Consider the integral from 4 to 13 of 1 over the cube root of x minus 5 dx. We do not see the infinity symbol there, but there is a hidden infinity. As x goes from 4 to 13, it passes through 5. As x approaches 5, the cube root of x minus 5 approaches 0. So 1 divided by that root approaches infinity. When x is exactly 5, the integrand is 1 over 0, which is undefined. This type of improper integral is less obvious. If you are not paying close attention, you might not even realize that this integral is improper. We start with the first type, with infinity in the limits of integration. Consider the function y equals 1 over x, which is sketched here. The integral from 1 to infinity of 1 over x dx describes the area between the curve and the x-axis, starting at x equals 1 and continuing indefinitely to the right. We have two challenges in this integral. We have to integrate, and we have to deal with infinity. Our strategy is to separate those problems and address them one at a time. First, we address the integration, integrating from 1 to some finite value I'm going to call b. b represents a point on the x-axis. The area from x equals 1 to x equals b is shaded in red. After we integrate, we will use a limit to examine what happens as b approaches infinity. The antiderivative of 1 over x is the natural log of x. We evaluate that over the limits from 1 to b, which gives the limit as b approaches infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0. So we have the limit as b approaches infinity of the natural log of b. This completes the integration part of the problem. We have found that the area between the curve y equals 1 over x and the x-axis from x equals 1 to x equals b is the natural log of b. Now we consider the effect of letting b approach infinity. As b approaches infinity, the natural log of b also approaches infinity. The area is infinite. This may seem obvious. As you keep taking b further out to the right, you keep getting more area. So taking b infinitely far to the right gives infinite area. Now we look at another example, using the function y equals 1 over x squared. The sketch is very similar, and the process is similar, but the result is a bit different. As before, the integral of the function from 1 to infinity represents the area between the curve and the x-axis, starting at x equals 1 and going infinitely far to the right. We use a limit to separate the problem of integrating from the problem of dealing with infinity. First, the integration. The integral from 1 to b represents the area between the curve and the x-axis from x equals 1 to x equals b, where b is some finite number describing a specific point on the x-axis. First we integrate, and later we consider the limit as b approaches infinity. To integrate 1 over x squared, we write it as x to the power of negative 2, and then use the power rule. This gives us negative 1 over x. Substituting in the limits of integration, x equals b and x equals 1, we get the limit as b approaches infinity of 1 minus 1 over b. For a finite value of b, the area between the curve and the x-axis is 1 minus 1 over b. Finally, we consider what happens as b approaches infinity. As b approaches infinity, 1 over b approaches 0, so our area is 1 minus 0, which is 1. This is perplexing. The graphs looked very similar, we approached the problem in the same way, and yet one gave us an infinite area and the other gave us a finite area. The first conclusion we can draw from this is that improper integrals are not all the same, even when they look very similar. We can get a clearer idea of what is going on with these integrals if we replace the rough sketches with better graphs. The red curve here is y equals 1 over x, and the blue curve is y equals 1 over x squared. While the shapes are similar, they are not the same. The area under the red curve, y equals 1 over x, as x goes from 1 to infinity, was found to be infinite. The area under the blue curve, y equals 1 over x squared, as x goes from 1 to infinity, was found to be 1. We can see in the graph that the blue area is much smaller than the red area because the blue curve approaches the x-axis much faster than the red one does. Think of a very basic model for area. The area of a rectangle is height times width. In these integrals, the width is going to infinity, which should make the area large, but the height is going to 0, which should make the area small. These two trends are fighting with each other. Sometimes one wins, and sometimes the other does. In this type of improper integral, the horizontal dimension going to infinity is the same in all the problems. The difference between one integral and another is the speed with which the vertical dimension goes to 0. In the red curve, y equals 1 over x, the vertical dimension goes to 0 very slowly, so it loses. The horizontal dimension going to infinity causes the area to go to infinity as well. In the blue curve, y equals 1 over x squared, the vertical dimension goes to 0 much faster, so it wins. The area is finite, even though the horizontal dimension is going to infinity. We will come back to this same idea in a later chapter when we consider infinite series. For the moment, what we need to know is that improper integrals are not all alike. The result is not obvious from the sketch, and we have to use limits to determine the outcome. My students should note that I do give points for correctly using the limit notation. I want you to show the steps in the same way that I show them here. You can't just do it in your head, because I can't see inside your head to grade your work. Before we move on to the second type of improper integral, I want to consider one more example of this type. Here we consider the integral from negative infinity to positive infinity of 1 over x squared plus 1 dx. Because we have infinity in two different places, we are going to need two different limits. We have to break this integral into two parts. You can break it anywhere you like, but breaking it at x equals 0 is convenient. This gives us two integrals, each involving infinity in one place. We evaluate these integrals separately and add the results. If either one gives infinite area, then the result is infinity, no matter what the other one does. This problem is symmetrical, so we expect to get the same area on each side of the y-axis. Just to check that, I'll do both parts. On the right side, we have the integral from 0 to infinity of 1 over x squared plus 1 dx. As we did in the previous example, we start by finding the area up to x equals b, as shown here in red. This is the integral from 0 to b of 1 over x squared plus 1 dx. Then we consider what happens as b approaches infinity. The antiderivative of 1 over x squared plus 1 is the inverse tangent of x. If you are not familiar with the inverse tangent, you can watch our video on inverse trigonometric functions. We substitute in the limits of integration to get the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 0. The inverse tangent of 0 is 0. This means the area between the curve and the x-axis from x equals 0 to x equals b is the inverse tangent of b. Now we are ready to consider the limit as b approaches infinity. As explained in our video on inverse trigonometric functions, the limit of the inverse tangent of b as b approaches infinity is pi over 2. The left side is similar, except that the infinity is in the lower limit of integration rather than the upper limit. We use the same strategy, but not the same letter. You should use the same letter only when it means the same thing. Instead of integrating from negative infinity to 0, we integrate from a to 0, where x equals a is some point on the x-axis to the left of x equals 0. We will integrate to find the area in green between x equals a and x equals 0, and then consider what happens as a approaches negative infinity. As before, the antiderivative is the inverse tangent of x. We substitute in the limits of integration to get the limit as a approaches negative infinity of the inverse tangent of 0 minus the inverse tangent of a. As noted earlier, the inverse tangent of 0 is 0. This means the area between the curve and the x-axis from x equals a to x equals 0 is 0 minus the inverse tangent of a, or the opposite of the inverse tangent of a. Now we are ready to consider the limit as a approaches negative infinity. As explained in the inverse trig video, the limit as a approaches negative infinity of the inverse tangent of a is negative pi over 2. Combining the two sides, we get a total area of pi. Now we move on to the second kind of improper integral, where the integrand approaches infinity. The integrand is the function inside the integral. Consider the example from the beginning of this video. The integral from 4 to 13 of 1 over the cube root of x minus 5 dx. As we can see in the graph, the function has an asymptote at x equals 5. Near x equals 5, the function approaches infinity on the right and negative infinity on the left. Exactly at x equals 5, the function is not defined. We break the integral at x equals 5 and use limits to avoid the problem spot. On the right side, we have the integral from 5 to 13 of 1 over the cube root of x minus 5 dx. The function is undefined at x equals 5, so we avoid that point. We let a be some number a bit to the right of 5 and find the area between the curve and the x-axis from a to 13. This is the integral from a to 13 of our function. To make the function easier to integrate, we write the root as an exponent. The cube root is the same as a 1/3 power. Because the cube root is in the denominator, the 1/3 is negative. Once we have this area, we will consider the effect of letting a approach 5. Notice that a is greater than 5 and will stay greater than 5 as it approaches 5. We indicate this by putting a little plus sign on the 5 in the same position where you would put an exponent. This is read the limit as a approaches 5 from the right. The antiderivative can be found using a substitution u equals x minus 5. I'm not writing that here because it won't fit. The integral is 3/2 of the quantity x minus 5 to the 2/3 power. We evaluate it from a to 13 and then consider what happens as a approaches 5 from the right. As a approaches 5, the quantity a minus 5 to the 2/3 power approaches 0. This leaves 3/2 of 8 to the 2/3 power, which is 6. Next, we consider the left side, where we have the integral from 4 to 5 of 1 over the cube root of x minus 5 dx. Again, we avoid the point x equals 5 because the function is undefined there. We let b be some number a bit to the left of 5 and find the area between the curve and the x-axis from 4 to b. This is the integral from 4 to b of our function. Again, we write the root as an exponent. Once we have this area, we will consider the effect of letting b approach 5. Notice that b is less than 5 and will stay less than 5 as it approaches 5. We indicate this by putting a little minus sign on the 5. This is read the limit as b approaches 5 from the left. The antiderivative is the same as before. We evaluate it from 4 to b and then consider what happens as b approaches 5 from the left. As b approaches 5, the quantity b minus 5 to the 2/3 power approaches 0. This leaves 0 minus 3/2 times negative 1 to the 2/3 power, which is negative 3/2. Based on the graph, we expected a negative area because the curve is below the x-axis. Combining the two parts, we get a net signed area of 4.5. Our last example is similar to the previous one, but different in a way that turns out to be important. Consider the integral from 4 to 13 of 1 over x minus 5 dx. As in the previous example, the function has an asymptote at x equals 5, so we break the integral there. On the right side, we have the integral from 5 to 13 of 1 over x minus 5 dx. As before, we let a be some number a bit to the right of 5 and find the area between the curve and the x-axis from a to 13. This is the integral from a to 13 of our function. Once we have this area, we will consider the effect of letting a approach 5 from the right. The antiderivative can be found using a substitution, u equals x minus 5. It is the natural log of the absolute value of x minus 5. We evaluate it from a to 13 and then consider what happens as a approaches 5 from the right. As a approaches 5, the quantity a minus 5 approaches 0. You may recall that the limit as x approaches 0 of the natural log of x is negative infinity. You can see that from the graph of the natural log function. This means the limit as a approaches 5 of the natural log of a minus 5 is negative infinity. Subtracting negative infinity from the natural log of 8 gives us an infinite area. When the integral is not equal to a finite number, we say it diverges. The integral in the previous example converged to 4.5, and this integral diverges. I've only done one side of this, but there's no point in doing the other side from x equals 4 to x equals 5. When one side diverges, nothing the other side can do can cancel that out to give a finite area. Now we look at these two examples together. The curves are very similar, but not quite the same. The red curve is y equals 1 over the cube root of x minus 5, and the blue is y equals 1 over x minus 5. In both cases, x stops at 13, so there's no way to get infinite area on the right end. The infinity comes into the problem in the vertical dimension, with that spike going up near the vertical asymptote. The width of that spike is going to 0 as the curve approaches the asymptote. Again, the vertical and horizontal dimensions are competing. This time the vertical dimension, going toward infinity, is trying to make the area large, and the horizontal dimension, approaching 0, is trying to make the area small. In the first example, in red with the cube root, the curve is very close to the asymptote, leaving very little area going up that spike. In the second example, in blue without the root, the curve is farther from the asymptote, putting more area into the spike. That is the difference between an integral that converges to a finite value, like the red one, and an integral that diverges to infinity, like the blue one. As you can see, the graphs are very similar. You can't tell just by looking at the graph whether the curve stays close enough to the asymptote to produce a finite area. That's why we have this process with the limits. Please show all steps clearly. This concludes our video on improper integrals by conceptual calculus. For more math videos, subscribe to our channel.